So this is about me. I've pretty recently left Google after being there for about 5 years. Background by training, computer scientist. Job titles I've held in the past include software engineer, performance engineer, and site reliability engineer. I was one of the contributors to the giant site reliability engineering book that Google put out a couple of years back. And I'm in the more recent Seeking SRE book as well. So what is a black swan? One of the speakers yesterday actually alluded to this. It's an outlier event. It's something that's very difficult to predict. And it's something that is severe in impact. So what is a black swan event in terms of our systems? The classic example of a black swan event in the financial world is the 2008 financial crash. And I think we're still very much dealing with the repercussions of that. It's something that at the time seemed highly unlikely. I mean, who would think that the markets would go down 50%? But people did predict it at the time, and people looking back on it kind of say, okay, well, you know, there was all these correlations at play. And that's kind of characteristic of black swans. You know, you can't predict when they're going to strike or exactly what they're going to be, but you know that there's, you know, looking back, there's kind of clues, right? So in terms of our systems, the outages that I've been looking at here are things that have taken down sites for multiple hours or in some cases days, things that have really affected the businesses involved. Most of us know that most of the time when we're on call, we get alerts. There's something relatively small, something's gone wrong, a disk is filled up, or some tasks need restarting, like things that we can deal with from our run books. These are our white swans. This image comes from Pixabay, where I was searching for swan images for this presentation. These are in fact geese, and I think these represent pager noise. Okay, so every black swan is unique, and you can't predict them, but we see patterns, right? And sometimes we can use those patterns to create defenses in our systems and in our processes. Black swans can become routine non-incidents. So back in the day, most issues caused to systems and to sites are actually caused by change. So we push a change to our binaries, or we flip a flag, or we upgrade an operating system, like we saw in the previous talk, or 2 talks ago, and something changes and something breaks. And I've seen research that indicates that this is the cause of the majority of incidents. So how do we defeat this? There's the practice of canarying. This is where you roll out a change to a small subset of your fleet first. You observe it. Are there performance regressions? Are we serving more errors? We're not trying to catch every specific instance of a software bug up front using code review, using tests. Well, we try, but we know we're not going to succeed. So we developed this generic defense of canarying, which lets us see these issues in production, but before they do too much damage. So this is kind of an example of a class of incidents that used to cause sort of black swan outages, but now they don't because we have canarying, which limits the impact in the first place, and as well as that, most companies now can do fast rollbacks for any changes that we introduce. So a black swan has become a nice yellow canary. So in this talk, I'm going to be discussing a lot of other people's postmortems. My last employer was not kind enough to do too much sharing of their postmortems. I don't want to cast any aspersions on any organization that I mentioned here. On the contrary, any organization that is good enough to share their postmortem is doing us all a service. All of us have got horrible, nasty problems in our systems. It's just that some of us have been lucky and we don't know it yet, or we're not talking about it. So absolutely no disrespect to any organization I mention here. So the rest of this talk is going to mostly cover these 6 subspecies of black swan that I have identified. Hitting limits, spreading slowness, thundering herds, automation interactions, cyber attacks, and dependency problems. So hitting limits. This can strike in many, many, many different ways, and I'm going to give a bunch of examples now. Instapaper, this was last year. And I remember reading this and like my toes curled and I was just like, oh no, those poor people. So they were running on Amazon MySQL RDS. Unbeknownst to them, they were backed onto a AXT3 file system, which had a 2T limit. They hit that, all of a sudden, their database stops accepting any writes. And it took them more than a day to get back up in a degraded mode, because what they did was they spun up a new instance. I think they were trying a couple of things in parallel, but they managed to get the most recent couple of weeks of their data onto a new install, and then they spent the next few days backfilling all their historical data. Sentry, they maxed out their Postgres transaction IDs, and I can spend a half an hour just talking about this because it's super cool, and I kind of love consistency models and things. But basically, there are Postgres assigns IDs to each transaction, and you have to reclaim the old ones using a process called vacuuming. And if the vacuum doesn't keep up with the way you're using the transaction IDs, eventually you run out, and Postgres will stop accepting writes. So it took them a lot of hours to get their database back in a healthy state, and to do so, they wound up having to actually truncate a table with ephemeral data in it. Spark Post. This was from a great talk that Jeremy Blosser gave at SREcon earlier this year. They're a bulk email provider. They weren't able to send any email for multiple hours. They have a pretty high DNS workload just because of the nature of their business. They had recently expanded their cluster when they were running in AWS. They expanded their cluster to be able to deal with more traffic, but it turned out that AWS had a per cluster connection limit, and they hit that totally unexpectedly, and that was bad for them. Foursquare, they had a sharded MongoDB setup. This one's quite old. But they outgrew the RAM on their box, and performance just went off a cliff because they were kind of relying on being able to have the latency from reading from RAM. The nature of the way they were storing their data meant that, and the way that Mongo stores data in kind of chunks, meant they have all these small records packed into fairly substantial kind of MongoDB data chunks, and it meant that it's not very good at keeping a working subset in memory. So they had to reshard while they were at full capacity, kind of load-wise, and that's not a good place to be. Platform.sh, they were down for about 4 hours in 2016. They couldn't restart their orchestration software after they were doing some maintenance. And it turned out that this is a really strange little problem. They had a library software that was querying all their Zookeeper nodes. That had grown since the last time they had restarted this software, and it was communicating through a 64K pipe. And what it would do is it would put all the queries in the pipe and then kind of commit. But what was happening is pipe was filling up, and then it would go, oh no, it's full and I can't write to this pipe anymore. So while their site was down, they had to go and find this problem, debug it, add a semaphore. Not a good place to be either. So as we've seen, limits problems, they strike in a lot of different ways. It can be system resources like RAM. It can be logical resources like those buffer sizes, like the transaction IDs. It can be limits imposed by providers, cloud providers, and other things besides that I haven't thought of or seen. So what can we do? So load testing is around for ages. I once spent a year of my life doing very little else but load testing. And a load test that doesn't involve write load is not a very useful thing for a bunch of reasons. So you should have write loads in your load tests. You should have a pretty good reproduction, ideally, of production as a staging environment. And you should do enough inserts that you grow your data sets past where you are right now. So you know if you're going to hit one of these kind of limits, right? And you should do this for your ancillary stuff like your Zookeeper as well. You should test startup and kind of other operations with larger data sets than you have now. And doing that kind of thing, you can catch a lot of these problems. Monitoring. If you know about a limit, so the Instapaper one is interesting to hark back to that. They had handed off the entire site to a different team who were operating it at the time that the incident occurred. So very possibly somebody knew about that limit years back, but there was no documentation of it, and the new people didn't know it was there. So the best way to document that kind of thing, if you know about it, is to put in an alert in your monitoring and document it, explain the nature of the limit and what the proposed solution is, and then if you've gone away and it's 5 years down the line, the people who get that alert later on will have warning and be able to do something about it. So, spreading slowness. So this is a pretty recent incident, hosted Graphite. AWS had problems, and hosted Graphite went down, but they weren't running in AWS. What happened? Basically, they had a lot of customers who were in AWS. Those AWS customers were still connecting to them, trying to send in metrics, as you would expect. But the AWS network problems were causing those connections to be slow. So what happened was the connections available on their load balancers were all getting kind of filled up and saturated because of these connections from AWS. So funnily enough, this was completely inadvertent on AWS and their customers' part, but this is actually basically a DOS attack. It's called slowness, and the Iranians used this in 2009. If anyone remembers, there was a bunch of protests around their election time, and the reason the Iranians used this is because it's a very cheap for you and lightweight way of taking down a site that's vulnerable to this. And they didn't want to congest their entire internet in Iran, so they just did this. So it was pretty cool. So, Spotify, this one's quite old. They had a playlist service that would give back details of a user's playlists. The service got overloaded because, I'm kind of summarizing this one. This is a fairly complicated one and had a bunch of different things conflated. I'm going to put links for all of these on a slide when I publish the slides, so you can go and read them yourself. But anyway, their service got overloaded because another service started calling it. They rolled back that change, but by the time they did that, another service had developed these huge outgoing request queues, and they had some verbose logging enabled, and basically the whole thing just jammed up completely. They had to put in temporary firewall rules and restart their services into a healthy state before they could start serving again. Square, their authentication system slowed to a crawl, and I think anyone knows who's run a site that if your auth system is bad, then everything is bad. The root cause was they noticed that their Redis cluster was badly overloaded, and the reason was they had a line of code, or a snippet of code, that was retrying a Redis transaction up to 500 times with zero backoff. So they had the thing just spinning their, or like DDoSing their own Redis, which, I mean, to be fair, I mean, I've seen equally bad things many times. So this is, this could happen to a judge, as we would say in Ireland. So, it's hard to defend against this completely, but guidelines are that failing fast is better than failing slow. If you have load on your service that you know that you cannot possibly ever serve, don't just have queues that can grow indefinitely. Cut off, have a way that your service can say, I'm overloaded, stop. Deadlines for all requests, into a service, out of a service. Don't just let things sit there and tie up resources if they're not progressing. Retries need to be super limited, no more than 3 as a rule. Use exponential backoff, so you might retry after 100 milliseconds, 500 milliseconds, 1,000 or 2,000 milliseconds. Use jitter because you don't want a wave of errors to turn into an echoing wave of errors after the backoff. So you got to smear it out. There's a thing called the circuit breaker pattern, which is basically where instead of dealing with retries on a per request basis, you put in a little widget of software in front that sort of sees all the requests going out from a particular client, which might maybe serving many, many user requests, to a backend service. And if it sees across all these requests that the backend service is not healthy, it'll fail those requests fast before they even go to the unhealthy service. So this is a good pattern. Another defense, USE dashboards, and these, as far as I know, were popularized by our co-chair, Brendan Gregg, so definitely have to give credit there. At the root, most of these problems are caused by something getting saturated somewhere. So the key to quick debugging and remediation is to be able to find what is saturated. So for all the key resources and for the services in your system, try and have these USE dashboards. They're super important. If you can pinpoint what is saturated, even at a high level, even if it's the level of a service, as opposed to whatever resource within that service is saturated, you'll get that sorted out much faster. There's nothing worse than sitting there, looking at your array of microservices that compose your site. Your site's at a crawl, and you don't even know which service is actually causing it. These sorts of gray, slow dragging errors can be really hard to find the root cause of. So this will really help you. Thundering herds. So a Richard Thaler quote referencing Taleb, from who this talk is named. A lot of this stuff happens because things are correlated in our systems. We think things are independent and really they're not. And this is true also of the demand on our service. So where does coordinated demand come from? It can be users. So sometimes, if you work for a company that does flash sales, and that's what I did when I did my performance engineering year, that was fun. There are certain companies, games companies, that only release in-game items for purchase once a month, and that can create a good old thundering herd. So that sort of thing can create coordinated demand from users. But more often, when we get a big spike of demand out of nowhere, it's from computers, because computers are good at creating coordinated demand. So a classic old school way of doing this would be having all the cron jobs in your organization kick off at midnight. Mobile clients are super dangerous. If you ever see any code where a mobile client is hitting a backend to update data at a particular time of the day, that's a bad pattern and should be smeared over a long period of time. Large batch jobs, like I say, I worked at Google, so we had to worry about people starting up, 10,000 worker map reduces, especially the interns. And if you've got a bunch of jobs like that, or tasks all starting at the same time, that can create quite a bit of coordinated demand. So here's some real-world incidents. So Slack, I was actually in the Slack office about 2 weeks ago in Dublin and talked about this incident, so that was cool. So Slack, by the nature of it, I assume most people have probably used Slack. It's sort of like a modern IRC. It uses a WebSocket space API, so clients have long-running sessions with the backends. They had to restart one of their devices, a server. It caused something like 13% of their user base to be disconnected, and they all reconnected right away. And in Slack's architecture, on reconnection, the client tries to query a whole bunch of stuff, like what Slack team, what channels are in the Slack team, what users are in it, what recent messages. So all this coordinated demand saturated their database. Circle CI. They are a continuous integration kind of build company. GitHub was down for a few hours. GitHub came back. And when it came back, obviously there was a big queue of demand on their service because it had been pent up while GitHub was down. But they had a problem where their architecture at the time, and they fixed this since, involved some really complicated logic when a build was enqueued, because it had to query a whole bunch of user preferences and what other builds were happening for that same organization or user. And the demand of trying to do that caused their database to get contented and saturated. And that was not good. So what's our defense against this? The real defense is to not fall into the trap of thinking, oh, well, how would I get a thundering herd to my service? Because as we've seen, there's all sorts of different ways that this can happen. The best thing is to plan and acknowledge that probably at some point there's a chance you will face a really big coordinated spike in demand. So think about degraded modes. If your service is too busy to serve, can you serve something static? Can you serve a smaller data set size? Are there some requests that you can drop? I mean, maybe you have a mix of batch traffic for analytics in your organization and user traffic. Drop the batch traffic, right? If you're kind of an organization like Circle CI, maybe you can queue input into some lightweight cheap queue and then do the heavy processing later, as opposed to having to do the heavy processing synchronously. So, and test it. Fundamentally, make your plan for what's going to happen when your service hits that big, overwhelming spike of demand, and test that your service is doing the best that it can do under the circumstances, whatever that plan is. What you want to avoid is what we saw before in some of these incidents where that big wave of demand causes your service to get in an unhealthy state with all these big long queues and all these unhappy locked up services. Because, even if you can't serve traffic, when that big spike of traffic goes away and things normalize, you want to get back to serving normally as fast as you can. And if your service has been sort of hammered flat by this wave of demand, you can't do that. Okay, automation interaction. So this is something that is maybe a little bit less common, but we're all doing more automation these days. It is a new thing, and it's great. I mean, we should be doing more automation, but it's not entirely it's not entirely safe, let's just say. So this happened in 2016, I think. I was at Google at the time. We disk erased all of the machines that run the content delivery network. It's quite a lot of machines. Luckily enough, Google had basically had planned that these machines were reducing latency rather than being something that absolutely had to be there for the site to work. So things were a little bit slower, and there was a bit more congestion for a few days until it was all rebuilt. But everything still works. So this is sort of a near miss. There's a whole talk that talks about this and also talks about automation safety. It was by Christina Skulman and Etienne Perrault at SRECon last year, I think. And I will link that in the slides when I put them up. But anyway, the TLDR is an engineer tried to send one rack of machines to disk erase. Due to an unfortunate regex incident, it matched everything in the world. And so we accidentally did the entire CDN. So yeah. Here's something a little bit different, but the same theme from Reddit. So they were doing a Zookeeper migration. They turned off their autoscaler because they knew that Zookeeper would not be in a good state to be read while this migration would be happening. But they have this automation that makes sure that their autoscaler is running. So it noticed that the autoscaler was down, and it brought it back up. And the autoscaler read bad data, and then it decided that it should turn off the rest of Reddit. So that was bad. So what is a complex system? A complex system is a system that has multiple parts that interact in different ways. Even what seems to be a fairly simple system, once you have even a few moving parts that can interact in different ways, the number of possibilities for things that can happen, sequences of events in those systems, is really high. So that's what we mean when we say that, or well, when Richard Cook, who was much smarter than me, says that complex systems are inherently hazardous systems. And once you start seeing any system that's got human operators and automation all working in it at once, you start seeing automation systems like playing whack-a-mole with each other. It's really funny. I mean, it's terrible, but it's funny. So what is the solution here? It's control. The recommendation is to create a constraint service that limits automation operations. So only allow a certain number per time period. Don't allow automation operations if the service is out of SLO. Set lower bounds. Say we need to have at least X many tasks running. Provide an easy way to turn that automation off in case somebody notices that it's not working properly. That should be any on-call engineer in your organization, not just your team. And all the automation should log somewhere so that you can see what's happening. A Slack channel works, something like that, your logging system, whatever makes sense. Cyberattacks. Not a security engineer, but it's still worth looking at this. This is the single most impactful incident in this presentation. Maersk are a global shipping company. They got infected by the NotPetya malware. This was last year. There was a big Wired article on this. It's a really good read. They didn't talk about it publicly. The Wired article was written because some employees leaked. They had to turn off their entire network for about 2 weeks. They couldn't unload ships or take bookings. It cost billions. They say it cost them about 300 million, but there were some big companies had to stop manufacturing because they couldn't ship. It could have been a lot worse. The human resilience of the employees at Maersk was impressive. They were taking orders using their own WhatsApp accounts and using Gmail and stuff. The defense here is minimize the blast radius. Separate your production systems from your non-production systems. Really, you shouldn't be having any random packet be able to go from the infected malware in your office to where your serving systems are. Google does a really cool thing. It's been written about under the Beyond Corp label. All the stuff, all the requests into production, all the traffic into production, like SSHs and everything, goes through proxies. So there's defense in depth here. Things are locked down at the network level, and then at the application level, only what those proxies allow can get in. And we can split up our production networks, if they're large as well, into global zones. I think there's going to be a lot of stories about those of us in operations working more closely with people in security, because we have the intimate knowledge of the systems that they need to do their jobs well. And there are certain things that they will not be able to do without operations people designing the systems in the right way and operating the systems in the right way. So this is, I guess, the modern thing. Like, we can't throw security over the wall to a security team, like the way devs couldn't throw systems over to an operations team. So, final one, dependency problems. So can you start up your entire service from scratch with none of your infrastructure running? This is the question that Tanya Riley asked last year in a keynote speech. Simultaneous reboots of your fleet can happen, and that's a very bad time to notice that your storage infrastructure can only come up if your monitoring is running, because it's, trying to find the least loaded thing to put its blocks in or whatever, and that depends on your storage being up, because that's where it's putting its data. You can easily get into these kinds of situations in modern microservices architectures. Here's an example. GitHub, January this year, they had a 2-hour outage. They had a power disruption, just a minor blip in their power supply. 25% of the boxes in their main data center rebooted. Some of their machines didn't come back. Their Redis cluster was unhealthy. So their Redis cluster was only supposed to be a soft dependency, just something that's nice to have. But unfortunately, that had unintentionally turned into a hard dependency. So they had to go and actually rebuild that cluster before they could get back up. Trello, there was a S3 outage. Their web app runs there. Their API should have been fine, because that's running in EC2, I think. And even if their front end is down, if their API is up, their mobile clients can use it and still function. But their API services were checking if their front end was up for just no good reason at all. So defense, layer and test. Decide what layer each service is in and only let it depend on things in lower layers. Test the process of starting your infrastructure up. How long does that take with a full data set? If you do this just in staging with a very small data set, you might think that you can start everything up in 5 minutes, but maybe in production that will take hours, and that's not a great place to be. Beware of soft dependencies. If you don't constantly test that somehow, that will turn into a hard dependency. So this isn't everything that can go wrong, because, well, time constraints. There's a lot of other ways that we can have very bad outages. But these are things that we can do something useful about. There are some general defensive strategies. There's a chaos engineering talk tomorrow. Disaster testing drills. Pick things that, you have strategies for how your system is supposed to work in various failure modes. Test that those work. Test that you can restart the thing. Fuzz testing ensures that your systems can't crash with unexpected input. So it's a technique where you generate ranges of input for your binaries, because you don't want a user to be able to reduce your capacity by crashing your systems. Should have an incident management process, and those are talked about everywhere now, but they're really important for this. Any on-callers should be able to get hold of executives who can make decisions, maybe communications people to talk to your clients. You need a pager alias that can get you a cross-functional incident response team. That's a really important thing to have. Don't rely on your own infrastructure to be there for you when you have a bad outage. There are ways that you can lose an entire network. Really, really scary things. So you should have some way of communicating that doesn't rely on your infrastructure whatsoever, even your network, ideally. A phone bridge is pretty good, maybe an IRC server that's hosted somewhere else. Try to make sure it's not something that has similar dependencies to your infrastructure. So maybe it should be a little bit further away from your main data center, so it's not using the same peering point. If you run on Amazon, AWS, maybe something that's running in AWS is not a great choice for you. So, ask your phone bridge provider and make sure they're not running there. Make sure people know how to get to it in an emergency. So laminated wallet cards are low tech, but that works, and practice. It's very hard to prioritize this work, and I'm out of time. Psychology, having a good incident management process really helps. It helps people deal with this. This is stressful stuff. If you're managing a team and somebody has just been through like a horrible day-long or multi-day incident, try and relieve them, and give the on-call shift to someone else and give them a bit of time off, because they're not going to be useful for a while. More reading. Michael T. Nygaard's Release It is a great book that has a lot of information on some of the things that I've been talking about. Not all, but other people's postmortems are always a great read. So Dan Liu's page is good, and sreweekly.com has fresh stuff all the time. And credits. And like I said, I'm going to put the slides up, and I'm going to link to all the postmortems I've talked about and some of the other talks and things that I've referenced here. So thank you very much.